Monday, because to a global failure, YouTube was not working well, but everything should be up and running again. So let's start the lecture. As said, today you get your Christmas present. I will give you some knowledge about something very important, and that is varioscale representations, varioscale geoinformation. And for that, two main structures will be introduced to store and represent the varioscale data. The first one is called the TGAP, topological generalized area partitioning. And the second one and related structure is called the space scale cube. And yeah, as you will see in the lecture, much of this is really research work, result of research work, even very recent. And it is a joint work with Martijn Meijers, who you know very well, Radan Suba, Dongliang Peng, and others. So, yeah, varioscale, we are all used to different map scales. You see a series of map scales for the same region, but presented now for comparison reason at the same scale, but in the labels you see the different scales, 1 to 25,000, 50,000, 1 to 100,000, up to 1 to 500,000. And you see that the more you generalize, the smaller the scale gets, the more details you have to remove to make it really simple. So this is called multiple representation or a multi-scale map. And there are many of them. So in this lecture today, I will first explain a bit more about the TGAP, the basics, the principles. Next, how to implement it in a database. Then something about how to use it over the web, discussion about progressive web transfer. Then a discussion on better quality of the map generalization, which is always an issue, the cartographic quality. And further, a discussion on the through smooth zooming. And finally, a discussion about higher dimensions. So until now it was 2D, the map, or 3D models. And 2D maps as presented are first discussed now. And we want to get rid of the multi-scale databases because they contain multiple representations of the same world. And this causes redundancy due to the fixed levels, and you're also limited to fixed levels. You don't see any content between the two levels. And if you zoom in, you could stop halfway and then you would not have an optimal map. So the purpose is to have a scaleless data structure, which is a single representation for all the scales, together with spatial access information, indexing and clustering information. And these data structures should give you access at any level of detail at any location. And so this is important. It's combined level of detail and spatial organization. What's also important is that most maps are used online and not on paper. That we want to do progressive transfer, meaning that, okay, first send quickly a first impression, an overview, and then if you have more time, send additional detail. And maybe you recognize that if you have a slow internet connection and if you look at a raster image, and perhaps you remember from the lecture last Monday, had a discussion about the data pyramids. And that means first you get the top of the pyramid, just a few pixels, to put it simple. And next you get more details at the bottom levels of the pyramid. So how can this be improved? We want to have one representation for all scales. Already quite some years ago, nearly 30 years ago, just after I finished my PhD thesis, I was struggling with this problem and came up with the generalized area partition tree as a structure. And I'll explain you later what it is. And in this structure, I store the polygons for every object only once to be reused at the different scales. It was just based on polygons and it was no topology structure. So that was improved together with a former master student, Maarten van Meij. And the gap tree became a topological gap tree where we have edges and faces. And yeah, here you see this structure. It's a bit comparable to the trick we did with time. So at the bottom there is a detailed two-dimensional map. And at a certain scale, so now the vertical dimension is scale, small objects will be merged into one object, becoming a bigger object. And that is repeated and repeated. And between the different scales, we reuse the geometry of the edges. And therefore also the faces, because the faces refer to the edges. There was some last redundancy left, and that was due to, okay, when we, for example, over here, merge the two top-level objects, we take away the boundary between them, then the adjacent edges will be replaced with a new edge. And you could say, yeah, that is a bit redundant because this new edge is very similar to the two previous edges. So that is one of the things that remain to be done. There is also a lot of redundancy in references between left-right references. And Martijn Meijers worked on this during his master thesis, 2006, to remove more of this redundancy. And okay, in the next slides, I will now show you how this structure is created, both looking at the faces and at the edges. And the idea of the T-gap is that you have true vario scale with very small steps between the different scale levels. And at the most detailed level, the base level, you have all the information about geometry and topology. And on top of that, you create a structure using links. So no new geometries are created. So this is a detailed map showing the boundaries, like A, B, C, D, E, and so on, showing the faces 1, 2, 3, 4, 5, and so on. As you notice, next to the faces, you see also a small number, and this is called the importance. And the importance is driving the process of simplification. So these are the edges and a bit of the faces and their importance value. Okay, how is this importance value computed? That is a function you can specify yourself, but I use the function, okay, I look at the area of an object and at the class weight. And the class weight may be application dependent, but So if you are in ecology, maybe forest and grasslands are very important, and so you give these class weights, these class a higher weight, so they remain longer on the map compared to the other objects on your map. But if you are a real estate broker, perhaps you used a higher weight for the buildings, so the buildings are remained longer. This is very important because the least important object will be removed. And if you look at all the objects here, you can see that object 6 is the least important. And when it's removed, we do not want to have a gap in the map. We want to take over this area by the neighbors. And okay, if there is one neighbor, there is no option, as in this case. So the neighbor is the area number 2. And that will take over the area of object 6 that's gone. But if there are more candidates, we compute the most compatible neighbor. And again, you can specify your own function, but the function we used a lot is look at the length of the common boundary and the class similarity. And you can imagine that different types of forests are more similar to each other than, say, forest and grassland, which is medium similar, but say forest and built-up area is even more different. And so the more compatible, the better it is to be merged, because you do less damage. But okay, here we have the first action. And after the simplification, we have one object less on the map. And this new merged object gets also a new identity, and also the new importance is computed. And what you also saw, if you careful pay attention, is some line simplification, for example, over here and everywhere. And so we get less objects and we simplify the edges, the boundaries. And now we repeat the same process. We look again at all the objects on the map and we say, okay, now this object, 0.3 is the least important, even if it's bigger than this one, but okay, this is apparently an important class. And so we remove now object 1, we look for the most compatible neighbor, and we look for the length of the boundary, we look at the class compatibility, length of the boundary, class compatibility, and then it's being decided that object 7 is again the best, most compatible neighbor. So that will be the merge. And now we have again one object less. And again, we can do line simplification. So this is our next simple map. And we keep on repeating. And now indeed, the small object is the least important one, object number 5. And it's being merged with object number 4. Something interesting is happening here. Because if object 5 is merged with object 6, you see that these 3 edges labeled with J, I, and J, G, I, and J, will now become one new edge, edge number N. And we only have 3 objects left. We can do line simplification, making it more simple. We repeat the process and so on until we have just one simple map. And you can say that's ridiculous, but okay, if you zoom out really a lot and the whole of the Netherlands would just be 1 pixel, you have to decide on the color, and that would be this color. Here I show now the gap phase tree. So that is the merging of the different objects. So in the beginning, object 6 and 2 were merged into object 7, and then 1 and 7 were merged in object 8. And on this side, we had 4 and 5 merging into 9, and 3 and 9 merging into 10. and finally 8 and 10 merging into 11. And the class that is winning with the different classes is indicated here with a color. So this is the finally winning color, this orange class, this one. You can also look at what is happening with the edges. In many cases, an edge is just being removed, then it's end of life. Let me go back to some examples. So this edge over here, edge number P, is being removed when the object 8 and object 10 are being merged, and it does not exist anymore. So that is object or boundary P, and it's the top of a tree in the edge forest, and this collection of different trees, edge trees, is called together the forest in the gap tree. So in total, gap tree forest. Usually it's a binary tree until a certain branch is stopping. But okay, I noted at this special case that it can happen that there are 3 or even more children. So it's not a true binary tree. The face tree is a binary tree, always. Okay, the line simplification. You may remember the different line simplification algorithms. And because we want to use the map at any scale, we don't know the target scale, and we also do not know the maximum tolerance we are allowed. So therefore, we compute the line simplification for every line. So here is line G with 8 vertices and a number of simplification steps. So this is the Douglas-Poyker simplification. This is the first simplification, straight line, and the most far away point is now number 4. So this is the second representation from 1 to 4 to 8. Then point 3 and point 6 are most far away, and they become the new, the next level of the simplification, and so on. And you can represent this generalization algorithm in a tree structure, and this is called the binary line generalization tree. And here you see it for 3 examples. In the nodes of the tree, there is the number of the point that is used to do the refinement from the baseline. So 4 is the first refinement, and then 3 and 6 are the next refinements, 3 and 6. And next to the number of the point, also the distance or tolerance. So 4 is 0.7 units away from the first approximation. And then point number 3 is 0.4 units away from the second approximation. And having this tolerance, we can traverse the tree when we get a request, okay, give me a line to be represented with an error no bigger than 0.5, for example. And then we know how far we need to traverse the tree. And we don't need to do the distance computations. We have the tree. We can also combine trees. So here we have 2 trees, I over here and J over here, and they have one common vertex in the middle. They call it vertex IJ. Over here, the distance to the first approximation from the baseline is 0.5 units. But we make this shared node at the top of the tree, and yeah, we have to give a guarantee of approximation when traversing, and then we can have this kind of mathematical expression. So we look at the distance from ij to the baseline, and we know both on the left and the right hand side what is about the tolerance at the top level, and we call that the error of I and the error of j. We take the maximum, in this case it's the error of j, and we say, okay, the worst case when we are not using any additional lines, so just the begin of I and the end of j is 0.5 plus the max distance of the edge at the right hand side, the j edge, because that would be this error over here. Okay, in reality it can be less, but then we have to do real new computations again, and we have to do the rebuilding of the tree. But if we do not want to rebuild the tree, but just combine the old trees and use this simple formula, we can do it very efficient. So this is the map, the small map, and on the right hand side we have the tree structures now depicted with the importance value, and you can also see that object 2 and 6 over here are merged in object 7, and object 2 and 6 exist until this importance 0.2, and then they stop to live. So 0.2 is the maximum importance of these two objects, then they don't live. Object 7 exists between 0.2 and 0.3, and after that it was merged with object 1 and it stopped to exist, and we got a new object, object 8. And so with these numbers we know in which importance interval which object should be shown on the map. So if we want to have a certain importance, say 0.38, then we look for the intervals associated with every node, and we select only the ones that are valid, and that are these 3 nodes, and they are in the right interval, and together they make a planar partition. And that is not a coincidence, that is the way we constructed it. Okay, later on, importance will correspond to a scale, a map scale, because I now depict it every time at the same scale, but when you make a simpler map, it is intended to be shown at a smaller scale, but it will be a larger area. So this is the foundation of the T-gap structure. Before a short break, I will also tell you a little bit about the implementation of the T-gap, and then we have a well-known 5-minute break. We want to implement it in an object relational database, say Postgres SQL. We can make new spatial data type. For example, make an BLG tree type that supports a kind of vario scale line. We make a number of different tables, a T-gap face table, an edge table, a special table for the BLG tree, and a node table. And we can use views and functions to avoid redundant storage. We use a functional index on the faces of the gap tree, and that is the extent, the bounding box, plus the important range where they are valid. So you could imagine over here, we have object 8 over here that has a bounding box in 2D, but it also has a scale range in the 3rd dimension. So it becomes a box in 3D, and therefore a 3DR tree is used, the 2D box and the important range. And we made implementations in different systems, Oracle, but also Postgres. Here are the tables, and you see the UML diagram. The face table, it has an identifier. Every object has an identifier. We have a bounding box. We have a total area, and we record the importance low and importance high. And we have a function, a method, that at a certain importance level can generate the geometry or a polygon. And so we can do a query and query this method of the face table later on, and that gives a geometry which can be colored. Okay, the face table has associated an edge table. And looking from the edge table, we have the same identifiers. The edge has also its own identifier, and an imp low and an imp high where the edge is valid. And it has a face on the right side and a face on the left side. Easy. There is no geometry over here, but the actual geometry is stored in the BLG tree table, which has again an edge identifier, which is the same as the edge over here. It has where the BLG tree is stored, and it has an importance. And we can get the geometry that belongs at a certain tolerance level to this tree. And we can do a merge of two trees into one new tree with the trick we shown before. And finally, we have nodes. And nodes are the end and the start of a line of a BLG tree. And the edge forest is, or the merging of two BLG trees into one is this representation. Two BLG trees become one BLG tree. In the case that we have three children, we repeat this trick twice, so we still make it at the end a binary tree because it's easy to represent. So in summary, the TGAP structure is implemented by a combination of structures with index structures. So we have a gap face tree allowing the face selection. We have the edge forest of the edges allowing the line selection. We have the BLG tree allowing line simplification. And we have the 3DR tree allowing fast selection of the area we want. Some practical example, a small data set in Amsterdam, both cadastral and topographic data. For the topographic data set of the region of Amsterdam, when it was stored as polygons, it was 82 megabytes. When it was stored in a topology structure, a lean topology structure, it became 107 megabytes. You could say that is strange because in a topology structure you store an edge only once and you are not repeating the coordinates of the shared boundaries. But okay, apparently the references and having more structure, more tables, not only polygons, but also a table for edges and a table for faces. And that caused this increase, factor 1.3. It's the same order of magnitude, but still. The standard Oracle spatial topology uses a representation that ended up at about 240 megabytes, a factor 3. A simple implementation of the TGAP structure caused the storage to be 690 megabytes, which is a factor 6. And that was a bit disappointing. And it can be explained when we look at the numbers. So for the basic topology, we have 170,000 faces, and that table needed 2 megabytes. We had 400,000 edges, and that needed 94 megabytes. We did not have a BLG tree, it was the normal basic topology. And we had a node table with 280,000 nodes, needing 11 megabytes. So in total, 107 megabytes. Looking at the statistics for the T-gap structure, the face table had a kind of duplication in number of faces. Yeah, and that is exactly what we expected, because in a binary tree, every time when you combine two objects, you get one object less. So the number of steps you have to do is exactly equal to the number of objects you have in the beginning, minus 1. So this number is exactly 2 times this number minus 1. Okay, that would be 4 megabytes, but we do store more information. For example, the imp low, imp high, the references to edges. Okay, that is also the fact for the other table, but okay, we needed really more here. We had really a kind of similar growth in numbers in the and the growth of numbers in the edges was not doubling like faces, but nearly 17 times more edges. And that was what we did not expect. And so we had a lot of new edges because of the merging, much more than we had new faces. And that also caused a lot of additional storage, 70 times more. We did not use 17 times more than the 94 megabytes, because here also the actual edge geometry is stored, and here not. In the T-gap structure, the actual edge geometry is stored over here, and here we see a more normal number, the number of BLG trees. And they are in the same range, 1.5 times, 1.6 times compared to the edges. And that is because of merging of edges and neighbor edges becoming one edge. Okay, and the nodes are exactly the same. But the pain is over here, in the high number of edges. So we call this an explosion. We made an additional trick for this, and we call that the lean T-gap. And with this implementation, and described in a paper in the GI Science Conference 2009, the total factor was below 2 of the normal topology structure. So that was quite a good price. So now you have a map at every scale, and you don't pay more than twice the storage. Okay, time for a quick break. And after the break, I will tell you a little bit about the data transfer between the server and the client. I'll stop sharing my screen for 5 minutes. So it is now 14:19, and we start again at 14:24 unless there are questions, and I see some questions in the gap. One question: what does the exponential indicate in the T-gap tree, the gap face tree? Guillaume, can you?
Yeah, it was back, I think, in the beginning of the slides.
Okay, I'll go back to
where you showed the image,
slides.
the gap history.
Go back.
Yeah. It's when you joined the faces, but when you went on a higher level, it had like a little exponential, like 2, 3, and 4. Is that
You mean these numbers? The little numbers?
let's see.
What slide was it? Do you remember that?
Can you share the screen and then I can?
Oh, okay. Yeah. I thought it was shared, but it's not shared. So I'll share screen again.
Yeah, go back.
So earlier than this slide?
Yes. Oh no, it's further. I think it's around. It's after the merging.
Here.
Slows, yeah.
Is it this slide or not?
Yeah, that slide.
Mm,
The number outside of the box.
this one.
Yes.
Yeah. This is an good question. To be honest, I have to think about it a little longer. So I will use the break time to come up with an answer.
Okay.
Okay, I will come back to you. Sorry.
No problem. No problem.
Okay, let's continue again. In the meantime, I did found the answer to the question, William. Yeah, these little numbers over here were from from the paper, and in the paper there was a little bit more discussion. What you could remember from the slides was that when two objects were merged, like 6 and 2, they had different classes. They had 6 had class W and 2 had class Y. The winner got the same class Y. And that happened again when 7 and 1 were merged. 1 had class X and 7 had class Y, and the result was class Y. Because 2, 7, and 8 have all the same class Y, you could actually say this is the same object for different map scales. And in the gap tree, you could also do, instead of creating new objects like 7 and 8, you could say, okay, I keep object 2, and then you would get this kind of tree structure. So 2 would have 2 children, 6 and 1, that were merged into this object. And at the other side, you see that object U is being merged with several other objects, V and object Z, and in the end also object Y. And the little number indicates that actually 7 is the same as 2, and 8 is the same as the original object 2, and the same for object 11, and that is actually an object 4, and 10 was object 4, but at the different scales. Okay, Guillaume, I hope this is clear.
Yeah, I think. Yeah, thank you very much.
Good, but I skipped this slide of the simpler tree. The simpler tree, by the way, is not a binary tree, and we really like binary trees. Easy to store in a database with 2 references, 2 children, the left and the right child. And when we get, say, more than binary trees, it's not so nice to store. Okay, let's quickly go to the new part, progressive data transfer. Yeah, this has to do with the internet, the web, the World Wide Web. Many people are using maps on their smartphone or on their laptop or tablet, and not so much on paper anymore. So it's important to support the internet or web use. And actually, this web technology is covered in a course later on in the geomatics program in the 4th quarter, where you get the course Geo 2007, calling GeoWeb technology, and you see the different components, HTTP, WFS. But what I would like to explain you now is that at the bottom we have this database where we store the TGAP data with the TGAP phase table and the TGAP edge table and the BLG and so on. And we realized 2 web services on top of the database. One was a very simple one that used the conversion to polygons at a certain scale or importance level. So when there was a query from the client, and we did it for a Google Earth client, and at a certain scale, we requested via HTTP GET a map, and then the web server forwarded that to a query to the database, and the result was then a set of polygons. So the edges and the faces were used via this function to create a polygon for a specific scale, and that was encoded as a KML. So KML is the encoding for 3D geometry on Google Earth, but it can also do 2D, and so it could be rendered on Google Earth. And Google Earth does not know anything about our TGAP structure or Vario scale or even topology, but you can use a topology structure here in the database at the bottom by using this server stack. We can also have more smart clients. We developed also a client that did understand the topology and the Vario scale, and then we sent queries to get geometry at a certain scale or a scale range. And we send back a set of faces, edges, Bell-Getris, nodes, encoded in the language GML, and the smart client is then rendering it. So this was the Google Earth client, and here you see a cadastral map with all kind of nice fancy colors, not having real meaning, but okay, you see the geometry, and you could zoom in and zoom out, and the map was changing all the time according to the TGAP structure. And in the database, when you request at a certain importance or scale, for example 1001, you do a select of the face, and you use importance level 101, and you want to have a polygon reconstructed from this face, and you return it as a geometry, as a polygon, from the TGAP face table, and you only select those faces where the importance is low is less than 101, and the importance high is smaller than 101, and then you get the proper faces. Note that I did not show the bounding box in the where clause, so this will return all polygons in our data set. So if it's a big data set, I should also add here and a bounding box is overlapping with our current window. What I can also do, so this gets me a slice exactly at the level 101. I could also get an ordered set of geometries and edges and faces belonging from very important objects until 101, so that it can be used for first showing the overview with the important objects, and then gradually showing more details until I arrive at the 101, which is the bottom for my map. And that can be done with this query. In the beginning it looks the same, but I send more information now. I send also the imp low and the imp high, so I know when to show this polygon. This is the same, this is the same, I selected from the same table, only the where clause is very different. I say, okay, the importance high has to be above 101, and I don't look at the imp low, and I order it. And so based on the incoming order, I can start drawing, and first an overview and then more detail. So that is not supported now by the current web standards. And again, in the course GeoWeb Technology, in Q4, you get more details. But the standard for web map transfer is called WFS, the Web Feature Service. And we propose that we extend this get feature request by a sort by clause. And to give you a bit of a flavor how it could look like. This is the WFS request with refinements. And so I get all the features, all the map objects, and I specify in what area, what box. And I also use a clause to say, okay, I want to sort it by the importance. Okay, that's one way to implement it. It actually works. So we built a viewer using SVG at the client side. It's now offline, but we did not maintain that viewer anymore. It was a long time ago, but we made a little movie of it so you can see it work. Actually, when you are zooming in, zooming out, two things happen. And we call that the graphic and the content aspect. And in the graphic zoom is enlarging. And so here you see my, in the center of the map on the upper left corner, you see a dashed area, and this is being enlarged to fill the gap over here. So this is pure enlargement. I did not any details, no more information. So this is the graphic zoom in, and I can have now more objects here because I have more space to depict things. So I add details. So this is exactly the same area, the map on the right side, upper right corner, as the map in the middle right, only with added content. And so adding more details. And here you can also imagine that you can do it in, so now it is done at once, all the details, but you can also, from this intermediate step to this step with a bit more detail, to this step with a bit more detail, to the final step with all the detail. And if you alternate a little bit of graphic zooming and content zooming, and you get a kind of animation going from this scale to this scale, and these two maps. Okay, one of our big worries is the quality of the map simplification, the map generalization. And we have been trying to improve that with different techniques. And the most important tool, of course, is the class importance and the class compatibilities. We can specify in the functions that I explained to you in the beginning that drive the T-gap creation. But it is rather difficult to get the output you want. And we thought, okay, is there not a better way? And because sometimes we get still merging of objects we would not like to merge. But okay, due to the rules we have, it will be merged and the result is not looking nice. So we thought if you can somehow use constraints that this allow us to do certain merges, we would get a better quality map. And these constraints, you have to create them. Either it could be an independent, smaller scale data set made by a human. You could say that's a kind of cheating because then you know the target, the generalized target. And the T-gap makes the little steps from the base map to the smaller scale data set and makes, say, better decisions. What we could also do and have been doing is also from the same source, directly go to another scale in one jump by optimization technique. This is hard computing, but in pre-processing that's allowed. So we know a good target, and knowing this target, we can use it to also take the small steps in between. And so here we see two maps. One is more on the left side, is more or less on the scale 1 to 1000. And on the right hand side, the content is according to the scale 1 to 10,000. Here they are shown at the same scale, but you can see the difference in content, details near the roads, details near the buildings, little paths, little extends to buildings, or little buildings are removed on the right side. So this is the detailed map, and the 1 to 1000 map, and it was in the area in Almere. And we also had the 1 to 10,000 map, and we use it as a constraint. And so this is the 1 to 10,000 map. And there are still some artifacts over here, things I do not like. These little things should be simplified. But by using the two inputs, we have now a data set where we have everything in between in the T-gap structure. Another thing is that the TGAP at the moment, at the initial moment, only supported area objects, but in reality there are also line objects and point objects. They do fit well in the table structure. We already had this table for the nodes and the edges, and we could not only use the nodes and edges to represent area objects in the topology structure, but the nodes and the edges could also be used to represent point objects and line objects, point objects and line features. So it fits really well in the existing structure and all other primitives. What it also allows us is to do a change of primitives. At a large scale map, many objects are represented by areas. But then at another scale, they may become lines. For example, a road is a polygon at a large scale map, but at a medium scale map and a small scale map, a road is just a line. And that means the same object can be represented by primitives of different dimensionality. And we can use this. For example, here we have a for object map, and object P1 is the least important, and it's a lake, and we do not want to remove the lake and assign it to one of the neighbors, but we say, okay, we did compute class compatibility. Let's sorry, we say first, okay, do not assign it to P1 or to P2 or to P3 alone, but let's subdivide P0 and give all neighbors a fair share. This was done by the triangulation and then the skeleton computation, that is the blue line in the polygon. And then the skeleton was made to connect with the outer edges over here. So now the blue lines meet at the outer edges. And then the parts, remaining parts, were assigned to the neighbors. Yeah, the nice tree structure that you are assigned to one neighbor and you get one new object, and that is now being demolished because instead of one parent, this object has now 3 parents. And because all the 3 neighbors got a part. So that is not a binary structure. So instead of a tree, a binary tree, it becomes a directed acyclic graph. And before, an object that was removed only had one parent. And when that is the case, when every object in the processing in merging has one parent, then you get a tree. And in the end, you have one object. But here, an object that is removed has multiple parents. So the light green, the yellow, and the dark green, P2, 1, 2, and 3. And that means that it is not a tree structure anymore. It's a directed acyclic graph. That's the effect. Okay, that is quite an implication. But this technique can be refined. Instead of doing fair shares, you can have multiple neighbors and many neighbors, not 3, but also 10 or and so on. But you can also do weighting of the compatibility. And so the different neighbors may be more or less attractive. And so neighbor C over here is less attractive and less compatible with the object that has to be removed. And neighbors B is the most attractive, has attractiveness value 7. And neighbor A is medium attractive. And the relative weights between the 2 opposite neighbors decide on where the cut is made on the triangulation to compute the skeleton. So you see the skeleton over here is really close to C, because this is 3 units, and over here we have 7 units of the triangulation edges. I hope it's clear. And the same here, we have the ratio 3 to 5, and here we have 5 to 7. And that gives a more fair distribution. Let's see. That is the T-gap. But we were still not really happy. Yeah, so the T-gap does a number of things. It can do a collapse over an area feature. A road may become a line. And so here is the road, and the area of the road is now being assigned to the multiple neighbors, the farmland, the forest, and the water, together with the original farmland and the bigger farmland. I think this is the bigger farmland. Is the parent of the road and the original farmland, or a part of the road. And the same for the forest and the same for the water. The second step here is we delete the forest. It's the second least important object. And so the forest is deleted and it's merged with the farmland into the big farmland. And in the end, we simplify the boundary between the water and the farmland. We make a straight line. And this T-gap structure can be converted into a 3D geometry, as you see over here. So at the bottom is the original map, and after every step you see the new representation. And here we have parent-children relationship in the T-gap structure. So the farmland here is the parent of the old farmland and the old forest. So it's over here. This is the farmland, and is the parent of the old farmland over here and the old forest over here. And so parent-child relationships become adjacency relationships, but in the vertical direction. And in the horizontal direction, it's the normal adjacencies, like the objects on the map. So now we can take slices out of this space scale cube, and then we get map at the proper scale. But okay, if we slice near the bottom and nothing happens until the road is collapsed over here. And it happens here, and then the map stays the same. And until the forest is being merged with the farmland, and then the map stays the same until the line simplification starts, and that happens here. And so when moving the slice plane up, we have sometimes no change or even a local shock from here to here or from here to here. So can this not be better? And the answer is yes. If we tilt the horizontal faces that cause the shock, because that ends one object and a new different object starts, and we replace the horizontal faces by vertical faces, then what we have is actually a gradual transition. For example, the road object is becoming a line, and you see it's going gradual. And after that, the forest object is gradually getting smaller, and the farmland is getting bigger. And also the simplification is happening gradually. And what's also really nice is that for every object, there is now one polyhedron representing it at all scales. So every 2D map object has a 3D polyhedron representing it at all the scales. So that is really nice. If we now take the slices, also over here at the bottom, where nothing did change in the past, now we see some small changes. The road is getting smaller and smaller. Over here we see the same for the farmland. And over here we see the boundary getting more straight from the zigzag to the straight line. And so that means a delta in scale or importance, and moving the slice pane a little bit results in a delta in the map. And the smaller the delta in scale, the smaller the delta in map. Really very smooth. We can do funny tricks. We can do also non-horizontal slices. For example, here, this corner very low, and then the opposite corner very high. What does it mean? Very low, a lot of detail, in the middle, average detail, and at the bottom, at the far end, low detail. And we made the space scale cube of a kind of checkerboard, which is difficult to generalize, of course, but we did it. And then when we took such a kind of space scale view, we got a mixed scale map from a checkerboard getting gradually more and more coarse. The nice thing is also this mixed scale map is a partition, and there is no overlap and there are no gaps. Okay, this is perhaps not a nice looking map, but it was also a strange question. If we do it with real data, and this is the German land cover data from the ATKIS source, and we take horizontal slices, you see at the bottom a lot of detail, in the middle less detail, and at the top the fewest detail. But we can also take diagonal slices. And you can ask, okay, why are you doing that? But okay, imagine all kinds of navigation systems where nearby you want to see a lot of detail, where you are now, and further away, gradually less detail. And so this is quite a nice function. Also the fisheye map that was already introduced by Lars Harry in 2002 as a kind of, okay, show me things nearby at a little different scale. So they are more made more important nearby things, and further away reduce the scale. This was only done with graphic content, but it now can be done with also with graphic scaling, also with content scaling. We can now add here also more content and not only stretching it. And that would be a bell shape. So, surface. And we implemented this also in an interactive system with a bit of topographic data. And with this, you can do a horizontal slice plane and you get a map like this. But you can do a local deepening. And near the yellow point over here, and also I think it's over here, you will see now more details, and actually displaying is higher elsewhere. This one is kind of lower. So elsewhere, the map has become simpler. So the buildings that you still see here, and also a bit details in the farmland and the forest are also lost, and the same at this side, a bit further away. So you can really do this well with this slicing technique. And this was implemented on the GPU. It was a desktop implementation, so direct on the PC. And you could drag the blue dot, and that means pushing down locally the slice plane or the blue dots. You had a number of dots you could play with, and you could move them around, give them different places, and then you were pushing down. And we made a video of this, and you can see it. Okay, that is the space scale cube created after the T-gap structure. But can you always create it? Can you always make such a transition which is gradual. Okay, let's have a look at a number of examples. One of the operations is a simplify of a line. So imagine I have a complicated line at the bottom, which have two vertices or three vertices, and at the top I want to make this a simple line of having just two vertices. And that means that this representation in the simple space scale cube with the horizontal faces would have two rectangles, rectangle 1 over here, rectangle 2 over here, and one triangle at the top. And that geometry would represent in this case scale cube the line simplification like this, from the 3 points to the 2 points. However, if you want to do it more smooth, you can replace the two triangles, the two rectangles and the one triangle by three triangles organized like this. So you remove the top, you make a triangle like this. So this triangle is vertical. Also this one is vertical. But the other triangle now here, that one is a tilted triangle. And if you now start cutting, you are generally gradually going from the 3-point line to the 2-point line, and so a simpler line. Okay, what about taking over the neighbor? A least important object is being taken over by a more important object. For example, this object to the right is more important, and this was the not so important object. When I have two objects that are neighbored, there is always a common boundary. So what I do is I connect the points on the common boundary to the point on the losing or the object that has to be gone. Sometimes the number of points on the common boundary and the opposite boundary are not the same. So I can make an additional, so I add here one more node because here I have one node in between and here I have two nodes in between. So I add one artificial node, I connect them and I triangulate. And I triangulate because I like to have the guarantee of flat planes. If I would not triangulate, then the polygon with this dashed blue line, this little black line, this dashed blue line, and this long black line would be over here in space. Could be, say, twisted. It could not be flat. It might not be flat. When I make it triangles, so whenever I have the case that I have a polygon of 4 points, I split it by two triangles. And with this recipe, I can always make this gradual transition. So the winner on the right-hand side is taking over the loser on the left-hand side. So in a gradual transition. There are other algorithms possible. And a drawback of this approach is that I add a new vertex. Actually, that was not really needed. If I would map the two opposite vertices on the opposite boundary to the single vertex on the common boundary, then also it would be a valid transition. Here are some options of the different algorithm. So at the upper right corner, you see a set of the old classic space scale cube when the transition is sudden. And then you can move the slice plane and nothing will happen with the two objects, left and right. When we make this triangulation, you see that when moving up the slice plane, you see gradually getting the left or the gray object getting smaller and smaller. And also a bit of the shape of the boundary is kept. In the upper right corner, you see an alternative where we try to transition with a single flat plane. And when we move up the slice plane, you see a kind of artifact that the boundary becomes a straight line at a certain moment. And that makes perfectly sense, because if this is a flat plane, the transition plane, and it is flat, and the slicing plane is flat, then the intersection of two flat planes is a straight line. And here you see another alternative for a transition based on a different way of triangulating. And so now they don't reach the opposite sides at the same height. They are in a different order, the triangles. And when you move the slice plane up over here, you see at a certain moment I get two disconnected parts of the disappearing polygon. And that's not so nice. So we made some requirements. So we would like to introduce no new points. We would like to avoid horizontal faces because they give shocks. We would like to avoid the vertical face in the shared boundary. So here you have a little vertical face in the shared boundary, and that means nothing is happening for a while. And that is because this plane is flat. And yeah, nothing is happening. We would like to avoid having intermediate multi-part objects, an artifact. We would like to have constant steepness of the transition, and that means also that the tilted plane has to have a constant orientation and angle, but that means a flat plane, and we saw that is for different reasons not good. And so we would like to keep the shape of the boundary of the faces, because that is important to be able to recognize objects, and of course no topology error. And here you see another example of a single flat plane transition. But it's impossible to have all these objects having their requirements met. That is not feasible.
Oh, excuse me?
Yeah.
I actually have a question.
Yeah, please go ahead.
So that is, I'm wondering if you move gradually the scale like we're doing in the models right now.
Yeah.
But are we in the transition phase? The scale is not really changing. It's just the geometry of the polygons changing, right? Because you still have the same level of details, and it's just the geometries which change.
Correct, but actually in the use later on, we will do the two things at the same time. So we will move up the slice plane, and we will do also the geometric extension, shrinking or growing at the same time. So these two things will happen in parallel, but now in the explanation, I kept in these little pictures. Yeah. I kept the scale the same, and to be fair, they should be getting smaller and smaller, because at the bottom where there's a lot of detail, this is for the large scale map, and at the top it is more the small scale map, though this is just a small step.
But isn't it, to be like very strict with it, isn't it all still the same scale? It's just like the slice is getting smaller?
I depicted it at the same scale, but later I will give you a real live demo where we show the content of the space scale cube. And when we interact, we are also changing the scales. And we have a kind of user interface for that. And you can also try it yourself, because these prototypes are still operational.
Thank you.
Okay, I hope it's clear, and otherwise wait, and I hope it becomes clear. Okay, the objects I showed now were perhaps a bit simple. And this kind of transition does not work if the losing neighbor is not convex. I cannot connect the points on the shared boundary, that is now in this case here. The top one is the loser, directly with the vertices of the opposite boundary of the loser. And the same is true when there's a hole. And in such a case, to take over the neighbor, the trick is to subdivide it into convex parts, and then you can take over part by part and triangulate. Okay, now using the space scale cube. Okay, a simple slice. This is the cube, this whole thing. We are at a certain scale and we want to have a certain extent, x and a y extent, and we can specify this by this slice. We could do it also a little different to create this initial map. So again, we have this area over here, but we do not take it just at this scale, but also at the top scale. So that is the smallest scale with all the detail. And we get it from the importance representation to the more detailed representation. And we add this detail in the rendering. And when you would have a slower internet connection, you would see then that the final map at the scale you want, at the area you want, is being composed in an animation. In total, this transmission of data is a bit more than this slice. You could say it's about a factor 2 more data. But the benefit is that you can quickly draw over here, because the overview is just probably a simple polygon and you have already an image. You could do a zoom in, and that is, you are at the top level here, the top scale, the small scale, and you zoom in to the larger scale, but your computer window is not changing the size, but when you zoom in, that means the area in the real world becomes smaller. And so actually you would like to have this upside down truncated pyramid to be retrieved from the server and sent in sorting based on the importance, and then you can draw. You could do also a zoom out, and then from your dashed slicing plane here, you go to the dotted slicing plane, which is at an even smaller scale. That means the area gets bigger. You can show a bigger area, but with less detail, and you want to do it also in animated style. That means send the content in this truncated pyramid again upside down. You can also do panning, a slice panning, or a panning with, say, a progressive rendering. You just retrieve the new part because you already had the old part. Time for a demo, perhaps after the break. It is, it's now 8 after 3, so 15:13, we continue for the last part of the lecture. So see you then. If there are no questions, I will check the chats. And I don't see any more questions in the chat, but please also interrupt me. So see you at 15:13 for the last part. Okay, welcome back. Let's continue with the demo. And okay, this is a web-based demo, our first web-based demo, so it's a bit simple. But you can see when you zoom in, you get more objects. You can also, if you look careful, you can see that area objects, it's not, the buildings are the most clear. You also see area objects being removed or merged with their neighbor. And so now this is the TGAP at work. And the way it's done is by slicing the cube. And that is done basically by the GPU of your browser, of your computer, that the web browser is using. And so that was this demo. Just a small area, a couple of years ago. And there are some more boundaries of the different data sets. For example, the German land use data set. And maybe you noticed that this demo, we had no casing. So the area objects did not have their own boundary line, which does not look so fancy. And this German demo had this casing. I will not do all the demos because it will take me too much time. We also worked on bigger data sets, for example, not a small 9 by 9 kilometer, but say a whole province. And that was achieved last year. And that was by chunking basically the organization of the space scale cube and sending them to the clients based on the chunks that are needed. But again, more on this will be explained in the web technology course. And hopefully by then, a space scale cube of the whole of the Netherlands. We are still struggling. Okay, maybe you noticed when zooming in, zooming out, we first, yeah, it was kind of smooth, but the animations still has a little bit of shock, of shock changes. And the course is, yeah, to our opinion, is the one-by-one approach in the TGAP. So we treat object by object by object. And we thought, if not processing one object and then do another object sequentially, but if we can process 2 objects or 3 objects at the same time, then every operation has 2 times or 3 times more time to take place in the change. And when we are now removing houses, it really happened gradually, but you did not see it because it goes so quick. You just see the houses removed. It's an all or nothing change, a bit like the classic space scale cube. So instead of merging just one object in a step, we could do multiple objects, for example, 2. And of course, we have to be careful that we maintain the topology correctly and avoiding neighbors. But if we have 2 steps at the same time, in the animation, the transition could take twice as long and giving the same content effect at scaling. So that is quite a big change. And we developed also a tool to see the difference between the single step merging and the parallel merging in the same small area. And we also developed a tool with this slider in the middle where you can see the difference. Let me try if it works. Yeah, now loading the data. The slider is over here. Data loading always, but it takes time. Okay, here the data is. And so both maps are changing, and I say both maps because they are different maps, and they do not look so much different. But look, if I now go over the slider, you see that different decisions were taken, and also look careful at what happens to the areas. On the right hand side, you see them, for example, the green areas. You see the transition here, smoother, and on this side you will, this is the left hand side is the one step or one generalization action at the time. It's the same small area. And there are differences. You can also compare them. Okay, at this scale there are not so much differences, but at some other scales there are differences. Okay, and also these tools to be able to compare the content is a part of what we developed the last couple of years. Both are here. So this is the nice slider compare tool. On the left you saw the single merging, and on the right you saw the parallel merging. We also developed some more web tools. And besides the normal slider, we had the juxtaposition. That means, okay, basically you show the same area twice, once left and one right. And so with the slider, it's not the same area. You have a cut in your area and you're moving that cut. But with juxtaposition, you are looking at the same area left and right, only with the different approach. Say the parallel or the single step simplification. We had also options for multiple map layers. You could say you have a topographic map as a background layer, and on top you could show a thematic layer and combine layers. We also added legend options to explain what is in the thematic map, and there are options for setting the visualization, the transparency of object if you combine layers on top of each other, switch on and off layers, change the thickness of the casing and the speed of the zoom and the pen. And you can scroll by your mouse wheel or by clicking the plus and the minus window buttons. So here you see that the two maps you see left and right here are of the same area. And in the implementation, we made this a multi-scale map with a discrete number of scales as listed here at the top. And on the right-hand side, we had the vario scale map. And okay, this I will also do a demo of this one. This takes some loading time. You will see at the top also that there are quite a lot of setting options which you can already use. For example, you have this zoom button here. And if you compare, and I can also go back again, then what happens left and right. And so left is basically graphic zooming and changing the content at a certain moment, and right we have the vario scale approach. So that is zooming with the plus and minus button. But you can also, of course, zoom by scrolling the mouse wheel, and then you can stop whenever you want. And you see on the right-hand side there are details being added, and at a certain moment the multi-scale map gets also the additional detail, but at once. And that's then repeated. The white areas are due that we have to wait until the new data is being arrived. Okay, other things we can do with the settings are, for example, changing the casing width or the boundary width. So you can make it very fat lines or very tiny lines or no lines at all. Yeah, with the zoom factor is how much it will be zoomed when you click a plus or a minus. The zoom duration is the speed or slowness. When you now zoom, there is a certain delay after you release the button. And that is the same for the panning. You can also do panning and it can be faster or slower. And you can switch on and off layers. And we have this juxtaposition. So you have a set for the left and a set for the right. So here we have two layers, the multi-scale topographic map and a raster map. So if we switch on the raster map, then you see, if you look very carefully, you see some street names here and some buildings from the raster map. And when you make it more transparent, you see the pure raster map here. And you can make it also fully opaque and or solid, and then you don't see the raster map. And so these are some techniques to play with it, and you can do also the same for the right hand side. So by having these tools, comparer tools, we are exploring the result of the T-gap and the space scale cube content when we created it. Okay, go back to the presentation. So this was the juxtaposition. So show two areas side by side, same area. And in this case, on the one side, it was the multi-scale, and on the other side, it was pure vario scale. Here we see another map. This is a thematic map about agricultural parcels and their dryness. And we can switch on and off also the legend. So the green is not so dry, and the lighter the green gets, the more dry it gets. And we also aggregate either by multi-scale steps or vario-scale gradual steps. You can also try this demo yourself. And when you click on legend, you can switch it on and off. I will not explain it further. And I also explained this setting option. By clicking in the upper right corner, you can either hide the settings or get the settings back, the interaction settings. So this gives us a good tool to play with the vario scale. Okay, to conclude, I would like to also have a look to not only two-dimensional maps, but also 3D models. And you could say what we did was we added dimension. So from a 2D map, we made a 3D representation. From the 2D polygons, they became 3D polyhedrons. The same is true with higher dimensions. If you start with a 3D model, you already have polyhedrons, for example, for the buildings or for the trees or for the forest. And you make out of them 4D, say, hyperpolyhedrons that are valid in a scale range and changing also in that scale range. The benefit of this approach, that we add the dimension to an object and represent with that all its stages, is that it is not redundant. The object is only represented once, and you have all geometry there and all structure there to select it and to visualize it. And it's also very well suited for web-based environment. So there's many benefits for the map producers. They don't have to make maps at all the scales anymore. Less manpower, less work to produce the maps, so more profit. Also, for the ones who are delivering the map, like the internet providers, it is more efficient. In total, the storage is less than of having many independent maps. Okay, by the way, the benchmark, you could say, is Google Maps. If you look, because if you zoom in, zoom out, you can say that looks smooth. In reality, it looks smooth, but they use 18 different maps, and they use a kind of graphic tricks to blend when you go from one level to another level. But in reality, there are 18 different levels, and it works well because Google uses a lot of resources, a lot of storage for the 18 levels. They have a lot of service and a lot of electricity. They are near the power plants, but it can be better. You can do it with less storage, less data transfer, or higher speeds, if you want to put it in another way, and have more functionality, better gradual content. Also, you can have this mixed scale view, the tilted views. And for the, that is what it brings also to the user, more functionality, less cost, higher speed. And we obtained a patent in the Netherlands and also internationally, myself and Martijn Meijers, and we made this open, so everybody can implement these ideas and, without being at the risk of having a legal problem. And they are protected by the patent. So if we look at what really happened, so we did add one dimension. So if you would start with 3D, we would end up with 4D geometries. But if we would start with changes over time, remember the last week when I was discussing changes in the 3D world, that would be a 4D partition of time and space. And if you would add scale to that, you would get a 5D topology structure, a really kind of tricky structure, but it does work. And it's important that it's a partition, and there are no gaps or overlaps, not in the space. No, there are no gaps in the map. All the neighbors are fitting together. No gaps in time, we did not forget, or there's no overlap in time, and the same for scale. So it's very well defined, even if we have funny extractions like in the mixed scale solution. Okay, to give you a bit of a flavor of how it could work in 3D, imagine we have two buildings at the largest scale, ZI and ZII, that's the first and the second building. One transition could be, okay, gradually move the shared boundary from the winner to the loser, and making the loser smaller and smaller. And then in the end, there is just one object. You can imagine that this is one option. There are different options. Here we have the shared plane again in black, and we map the shared boundary. We make some nodes in the boundary, and we map that to the opposite nodes of the loser, the same as we did in 2D. And then we gradually are moving these nodes to the opposite side. And that also means taking over the loser in a gradual manner. We could do that. Was the merge operation. We can also think about simplification. So this is the resulting object, the big ZII. Either we could simplify it and by pushing up the roof to a simple flat roof, or changing it into a diagonal roof, also a more simple roof, but tilted. That is the simplification in 3D. The ZII dash or ZII double dash are more simple objects than the starting object. Okay, how can you imagine this in 4D? Yeah, not. But I try to depict. So here I have my 3 dimensions, the X, the Y, and the Z. And you see the 2 objects here in the starting scale, scale 1. And you see here the winning object simplified at the starting scale 2. And what I know is that the object is kind of changed over scale, as in the space scale cube. And nodes and edges are connected. For example, the top edge over here is corresponding to the top edge over here. And this node is connected to this node. And yeah, this 3D polyhedron changing over the scales gives a 4D hyperpolyhedron or polytope. And the boundaries of this polytope, this 4D hyperpolyhedron, are, so the boundaries are 3D polyhedra. So at the bottom scale, this is a boundary. At the top scale, this is a boundary. And in between, there are volumetric boundaries, these composed of these dashed red things. That are, this is my dog, by the way. Come here. You can see this dog. He's getting bored. But here there are hyperboundaries. And a trend-scale 3-dimensional hyperboundary. So very difficult to imagine, but they are there and it does work. You can implement it. How could you implement it? We have some experience in the last lecture of the course, and that will be in January. I'll tell something about simplicial homology with triangles, tetrahedrons, and so on. Here you see some other options, but the idea is that if we integrate 3D space, time, and scale, we get a 5D representation. Okay, it is quite complex. Our databases do not support it well. Our GIS systems, QGIS or ArcGIS does not support it well. And so we have to develop a lot of solutions ourselves. But it is a very attractive solution, also especially in 3D. And so what I showed you in 2D about this perspective map, nearby, more detail, further away, less detail, that is actually the basis for all realistic 3D computer graphics in games or in animations. And also this solution with the varioscale, space scale cube or hypercube would support that. Okay, the implementation is a challenge. So from polyhedrons, we have to go to polytopes. We've been working on that. Regular polytopes, Rod Thompson did write his thesis about it, or simplicial homology, which is also proven mathematics that works in n dimensions, and we can apply to our geographic information data. And so we are exploring this step by step. And you may recognize some of the steps from the previous lectures and the current lecture. So today I focused a lot on 2D space and scale. I also discussed 2D space and time and 3D space and time. But in the end, somehow this is the ultimate goal. And we are then using 5D to represent 3D, time, and scale together. You can say, okay, I can have a 3D object and have an attribute for that, and I have another attribute for the time and another attribute for the scale or scale range. And that is not the deep integration. The integration is when you use a 5D geometry and a 5D topology. And yeah, to reflect on this, these concepts are enabling to store everything integrated and together. That means consistent, avoiding overlap of, or other errors, gaps, allowing zooming, allowing animations and changing in time. I showed it for topographic data and other type land use data. You could also use it for other types of continuous data. If you look at the reference for a geoscience type of data, like elevation data or flows in the ocean, Hugo Ledoux made a paper about this topic with Chris Gold, 2008 already. So with this, I would like to stop and wish you a very good holiday. Say best wishes for the new year. Relax a little bit. It was a strange year. I think strange for everybody. Try to relax with, if possible, the family and the friends. I know many of you are living quite far from your family. That may be more difficult. Anyhow, relax. I hope I also have some contact with your friends. Could be friends within geomatics. Thanks for your attention. I hope you like the content. Play a little bit with the links I included in the slides. They are really some fresh products. And you may have noticed I include quite often also work of master students. So this, what I present today, is now the work also of many master students in the past. And we have still plenty of challenges. So if you are playing and you are not happy with the tools, you can be the person that improves the tools in the future by smarter ideas. Okay, I now stop the lecture. I see no questions and only good holiday wishes. And let's hope that 2001 is getting quickly better. Bye-bye.